Welcome to this tutorial on empirical formula calculation. Today, you'll learn how to determine the simplest formula of a compound from percent composition data. This is a fundamental skill in stoichiometry that helps chemists understand the basic composition of substances. By the end of this video, you'll be confident in converting experimental percentage data into meaningful chemical formulas. An empirical formula represents the simplest whole number ratio of atoms in a compound. It's different from a molecular formula, which shows the actual number of atoms. For example, glucose has the molecular formula C6H12O6, but its empirical formula is simply CH2O. Notice how we've reduced the ratio to the smallest possible whole numbers while maintaining the same proportion of elements. To find an empirical formula from percent composition, we follow a systematic four-step method. Step 1, convert percentages to grams. Step 2, convert grams to moles. Step 3, divide by the smallest mole value to find ratios. Step 4, multiply to get whole numbers if needed. This methodical approach ensures accuracy and makes the process straightforward, even for complex compounds. Let's work through a real example. A compound contains carbon, hydrogen, and oxygen with the following percent composition. Carbon is 40%, hydrogen is 6.7%, and oxygen is 53.3%. Our goal is to find the empirical formula. Notice that these percentages add up to 100%, which confirms our data is complete. In step 1, we convert percentages to grams. Here's a helpful trick. Assume you have exactly 100 grams of the compound. This makes the conversion incredibly simple because the percentage values become the mass values directly. So 40% carbon becomes 40 grams of carbon, 6.7% hydrogen becomes 6.7 grams of hydrogen, and 53.3% oxygen becomes 53.3 grams of oxygen. In step 2, we convert grams to moles using the formula. Moles equals mass divided by molar mass. For carbon, we divide 40 grams by 12 grams per mole, giving us 3.33 moles. For hydrogen, 6.7 grams divided by 1 gram per mole equals 6.7 moles. For oxygen, 53.3 grams divided by 16 grams per mole equals 3.33 moles. Remember to use accurate molar masses from your periodic table. In step 3, we find the mole ratio by dividing each mole value by the smallest mole value. Looking at our results, the smallest value is 3.33 moles, which appears for both carbon and oxygen. Dividing carbon by 3.33 gives us 1.00. Dividing hydrogen by 3.33 gives us 2.01, which we round to 2. Dividing oxygen by 3.33 gives us 1.00. Our ratio is now 1 to 2 to 1. In step 4, we check if our ratios are whole numbers. If they aren't, we multiply all ratios by the smallest integer that makes them whole. In our case, we're fortunate because the ratios are already whole numbers. Carbon is 1, hydrogen is 2, and oxygen is 1. So no multiplication is needed. The mole ratio of carbon to hydrogen to oxygen is 1 to 2 to 1. Our final answer is CH2O. This is the empirical formula of our compound. It tells us that for every 1 carbon atom, there are 2 hydrogen atoms and 1 oxygen atom in the simplest ratio. This empirical formula could represent several different molecular formulas, such as CH2O itself, or larger multiples like C2H4O2, or even C6H12O6, which is glucose. Let's review some key tips for success. Always assume a 100-gram sample when working with percent composition problems, as this simplifies your calculations dramatically. Use accurate molar masses from the periodic table to ensure precision. Round carefully when checking for whole numbers. Values like 1.99 or 2.01 should be treated as 2. Finally, if your ratios aren't whole numbers after dividing by the smallest value, multiply all ratios by the smallest integer needed, such as 2, 3, or 4. With practice, this method becomes second nature.
If you like this video, Hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.